that I've been defining is H1 and H2 are subdirect factors. That's the term of art. So, why these matter? Subdirect factors matter because they'll help us break a cube up and analyze sort of individual components. The way I generate subdirect factors is by looking at the orbits of the cube. If we have a set 1 to the degree of the group D, then we look at the orbits under the group action of G onto this set S, and those orbits form tell us what the subdirect factors are. So anyway, let me move this out of the way, and let me also check my phone. We can minimize this, I think. All right. So, back to this example then. What I do in this example is I break up the cube into its subdirect factors. So like I said, for a Rubik's Cube, the 3x3 Rubik's Cube, one of the subdirect factors is going to be corners and one of them is going to be edges. I don't actually remember which A or B is corners or edges, but if I call example 3, we get both of these answers. Apparently A is the edges, so maybe I should say this: edges, corners. So if I do example 3 again, the first result here are all the edges. They've been renumbered in such a way that the edges are numbered between 1 and however many edges there are. And then the corners have been numbered from 1 to the number of corner stickers, I should say. Edge stickers and corner stickers. So indeed, this is a very useful function here. It finds all the block systems of all the finds all non-trivial block systems of each subdirect factor of the group. Let's see. Sorry, I have to check my phone periodically. So now that I've kind of explained what the use of blocks and how we've written code to compute block systems, I do have to optimize this a little bit. Right now, the algorithm is very inefficient. I wouldn't say very inefficient, but it's roughly quadratic. Mostly because in our algorithm, in a few places, we're doing linear search when we could be doing it in constant time and so on. So I'd like to clean up this code a little bit, and yeah, so we'll start there. So in this minimal block, maybe I should write some documentation. Find the minimal blocks of So we make these classes. Initially, I initialize all the classes to this. We're going to need to change our DJS data structure, I think. So destruct DJS to the parent, its rank, and its value. So I'm gonna take this out because this won't be true anymore. This isn't gonna be true anymore. We will do a new constructor of make DJS. This goes away. DGS parent goes away. Setf DGS parent goes away. DGS rank goes away. Setf DGS rank goes away. We do the same thing here. We will recompile this all at the end. Make DGS gives a parent, which is initially nil, so we don't have to set it. Its rank is initially 0, and its value is value. We want to set up the parent to itself, so we do that, and then we return itself. DJS find, that stays the same, and DGS union stays the same as well. However, what this does let us do is lets us optimize a few things. So we can recompile. Let's just restart this. Let's go to the file again. Let's hash plus ignore this, and let's go back up here. So we've gotten rid of our Stack Overflow. And now when we make these DGS things, we can encode their value in them. So what does that do for us? Well, it simplifies a few things, namely this rep call. When we want to find the representative of the equivalence class under the minimal block relation, we no longer have to find the position in the class. We now just do DJS value of our object, which is DJS find, which is the class of our parent. So even with that simple change right there, we should get a more performant thing. Oops. Let's compile these back in. And we still appear to get the same results. Let's do example 1, because that's kind of my little test. Except I didn't call it example 1, I just called it example. And that's still correct. So we've made that a bit better. Unfortunately, my union find algorithm is not the most efficient. So these fast versions actually do the fast version of union find. However, the algorithm doesn't work when I do the fast version because we need to change the representative of a class kind of dynamically. And with union find, the representative of a set changes. No, I did not check the time before or after, but I am going to assume that since the computational complexity went down, that surely it must have been faster. So ultimately I will want to use these fast versions here, but I'm going to hold off on that until I make this algorithm down here cleaner. So first we want to ensure that alpha 1 class is the representative of union. Right now that's sort of implicit in our this is implicit in this call. So let's see. So we initialize all of them. We initialize all the alpha classes, and then we go through the main algorithm. So this algorithm is ugly. It is gross. We have all these increments everywhere. We have these vector push extends. Just, it's pretty awful. What we need is a simple queue. What I'm going to do, let's see. I could quick load something, or I could just make the queue myself. Let's see, QL system apropos queue. So I have no idea. I mean, this is a typical Lisp thing. Which one of these do I choose? Alphas are the elements to this block system. So when I want to find a minimal block, for example, of the cube, what I do is I say find the minimal block containing this sticker and this sticker. And ideally what the output is all three of these stickers and then all the other corners of the cube. So the alphas are the individual stickers. You give it 2 stickers, you can give it as many stickers as you want, and they'll find a block that contains those stickers. So let's try loading queue. So queues, what do I do? Simple queue. Do I have any make functions? Make queue, queue, simple queue. Does this work? So now can I do it? See? Okay, I know I'm not reading the documentation of this, but it just makes me not want to use it if I can't. Okay, so queues make queue, and we give it a simple queue. I don't like that, but I guess it works. What do we have? Queues. Do we have a push? Queue push. Queue. Let's see. Let queue. Queues make queue. Simple queue. Queues. Queue push. Q1. Queues. Queue push. Q2. Do I have a queue empty? Nope, I do not. Yeah, I'm tempted to just write my own queue. I'll try to be a good citizen though and not do that. Queue top.